Okay, so last time we mentioned Gram-Schmidt, and let me just remind us how that works. I think what today we're going to do is work out an extended example, and then we're going to step back, look at it, and be like, whoa, something cool is going on here, right? So Gram-Schmidt is a way to take a basis and turn it into a, I always spell this wrong, M-I-D-T, Schmidt, and turn it into an orthonormal basis. So the idea is you begin with some basis of your n-dimensional vector space, and today we can just think of our vector space as being Rn or Cn, although it works in general. So you have some basis v1 through vn, and your goal is to turn that into an orthonormal basis. That is a basis where any two vectors are mutually orthogonal to each other, and every vector is a unit vector, so the norm on any vector is 1. So we want to turn this into an orthonormal basis, W1 through Wn. Okay, so that's the goal. And Gram-Schmidt gives us a process to do this, where it says, well, I'm not going to call these W. I want them to be unit vectors. So I think it'd be better if I call these U. Let me call them U1 through Un. But the way you do it is there's an intermediary step of you just make them orthogonal before you make them unit. So you begin with V1. We're going to make W1 just equal to V1. But then we're going to make W1 into a unit vector by calling your first unit vector just V1 divided by the norm on V1. So now that has unit length. So this step seems kind of useless, but it's setting up a pattern we're going to follow in general, because next we're going to define W2. Well, I want it to be like V2, but my problem is V2 may not be orthogonal to my first unit vector. I want this to be orthogonal to this guy, and then I'll turn it into a unit vector. So it's like, how do I make this orthogonal with U1? Well, I want it when I take the dot product, or more generally, when I take the inner product between U1 and V2 to give me 0. But right now, when I take the inner product between U1 and V2, I don't necessarily get 0. I get whatever the inner product between U1 and V2 is. And so what I do is I just subtract that. Let's just subtract the inner product between U1 and V2. Oh, wait, this doesn't make sense. What is a vector minus a scalar? So let me times this by U1. And now you think about it, what happens when I take the inner product with U1? Well, if I do U1 inner product with W2, that's just by linearity in the second argument. That's just the inner product of U1 with V2 minus this scalar, U1 with V2 pulled out, times the inner product of U1 with U1. But we say unit 1 is a unit vector. We built it to be a unit vector. So the inner product of U1 with U1 is just 1. So times 1. So we've built this just to be something minus itself, which is 0, right? So this is how this process works. So now we've built W2 to be orthogonal to U1, but it's not necessarily a unit vector, so we can just turn it into a unit vector where we're going to say our second unit vector is just W2 divided by its norm. And then we just continue in this way. What should W3 be? W3 is just going to be V3. Oh, but wait a second. V3 may not be orthogonal to U1. So how do we make it orthogonal to U1? Well, if I do U1 inner product with V3, I get something that may not be 0. U1 inner product with V3. So let me subtract off a copy of U1 inner product with V3. And I'll have a U1 here. So now when I do the inner product with U1, you'll just get U1 inner product V3 minus U1 inner product V3 times 1. Right? Just like above. And then it's like, great, now we've built this to be orthogonal with U1, but how can we also make sure it's orthogonal with U2? Well, I'll add a second piece. Well, it's just going to be exactly analogous. It's going to be U2 inner product with V3 times U2. Let's make sure this doesn't mess up the first thing. If I inner product this guy with U1, this piece doesn't change anything because U1 inner product with U2 is 0. So that will vanish. So we're still good there. But now if you inner product this with U2, you get U2 inner product with V3. Here you get 0 because U1 inner product with U2 is 0. And this becomes 1. So you end up with U2 inner product V3 minus U2 inner product V3, which gives you 0. Right? So these are just little correction pieces, these little correction terms that are making sure that we build this guy to be orthogonal to the previous unit vectors. And then once you have something orthogonal to them, you can then turn it into a unit vector. And you can keep going this way as long as you want. Like now you see the pattern, right? So you can keep going this way. So we'll define this to be W3 divided by the norm of W3. So keep doing this as long as you need to, for however many n you have. So I suppose in general, we could say, what is WK? Let's give a general formula for it. Well, it's just VK minus inner product of each of these u's up to k. So the sum from j equals 1 just prior to k up to k minus 1 of all the previous u's of uj inner product with whatever this v is, with vk. That's what a general expression is. And then we just define uk to be the unit vector. So turn this then into a unit vector. Okay, so that works. That gives you an orthonormal basis following this Gram-Schmidt procedure. Yeah?
Times uj argument?
Times, oh, very good, yes. These are scalars, right? You can't subtract scalars from a vector, that doesn't make sense. This should be times uj. And then that works because if you take the inner product of this with uj, that just becomes 1. If you take the inner product with something other than j, that vanishes. And so it works out just like we want, just like here. Okay, so that's how Gram-Schmidt works. But I think it'd be nice for us to see an example. So let me give you a concrete example. Let's say, let me just begin with 3 vectors. Let's say v1 is the vector 1, 2, minus 2. Let's say v2 is the vector 3, 2, 2. And let's say v3 is the vector 3, minus 2, 1. Note, these are vectors in R3, right? But this process works with arbitrary inner products over any inner product space, right? You can do it over the space of polynomials, over the space of n by n matrices, whatever inner product space you're interested in. But let me just do a concrete example. So here our inner product is just going to be dot product. And let's go ahead and calculate this, right? So this is going to take a few minutes, but you know, builds character. So here we go. W1. And I'll check here to make sure, you know, we're doing things correctly. I did this out last night, so if we make a mistake, you know, hopefully we'll catch it. But here we go. W1. You help me. What is W1?
V1.
Well, it's just V1, so that's not very interesting. But what is then U1? Yeah, it's like, what's the magnitude of this guy? Well, dot it with itself, and you get 1 plus 4 plus 4, that's 9. And then you take the square root, right? So we call the magnitude of something like W1 is just equal to the square root of the sum of the entry squared. 1 squared plus 2 squared plus minus 2 squared. That's exactly the same thing as just the square root of w1 dot w1. That's how we define this, where here our dot product is the inner product we're working with. So this comes out to be just 4, 4, 1, 9, square root of 9, 3. So we need to divide this by 3. So it's 1/3 of whatever the vector was before. Good? Okay, what is W2? Well, I want to begin with V2, 3, 2, 2. I want to subtract, let's look at this, U1 inner product V2. U1 V2, what is the dot product of these guys? Well, let's think. 1 and 3 is 3. 2 and 2 is 4. So 3 and 4 is 7. 2 and minus 2 is negative 4. So we're back down to 3. Times 1/3, that's 1. So here, our U1 dot V2 just gave us 1. And then we want to times that by U1. So times that by 1/3, 1, 2, minus 2. And that's it. So what do we get? 3 minus 1/3 is now 8/3. So it's 8/3. 2 minus 2/3 is 1/3? No. 2 minus 2/3 is 4/3, right? Right, am I doing this right? I hope so. 2 minus, 2 plus becomes plus because of the minus. 2 plus 2/3 is 6/3 plus 2/3 is 8/3. I think we did that well, right? Good, okay. That's what I did last night too, so I think we're on the right track. So then U2 would be, okay. Well, here's a little trick. Instead of figuring out what the norm is and then dividing by the norm, first scale it to something nice and then find the norm of that and turn that into a unit vector. So let me just scale this into something nice. Like, let me scale it into like 2, 1, 2. And now let's turn that into a unit vector, right? So what's 2, 1, 2 turned into a unit vector? Well, that's going to be, norm of that is 2 plus 2 plus 1. 2 squared plus 2 squared plus 1 is 9. So we're dividing by 3, so it's 1/3. You happy with that trick I just did? I just scaled it to something that looked nice, and then I turned that into a unit vector by dividing by its magnitude. Okay. And now let's figure out what W3 is. W3 is, we began with V3. 3 minus 2, 1. Now we want to subtract the inner product of U1 with V3. That is U1 dot V3. So let's see what that is. 3 minus 4 minus 2. I think it's negative 3. Times 1/3 is negative 1. So we're subtracting negative 1. And then we want to have our U1. So U1 is right here. It's 1/3, 1, 2, minus 2. And then we want to subtract U2 V3. So taking the dot product of U2 with V3. So here we get 6 minus 2 plus 2. So that's 6 divided by 3 is 2. And then we want to times that by a copy of U2, which is 1/3 of 2, 1, 2. Whew, I'm going to mess this one up, but let's try. 9/3 plus 1/3 is 10/3, minus 4/3 is 6/3, or 2. I think I should write it as 6/3 because I think it's going to come out to be thirds again. Negative 2 plus 2/3, so that's negative 6/3, plus 2/3 is negative 4/3 minus 2 is negative 6/3. Hope I'm doing this right. 1 minus, so 3/3 minus 2/3 is we're down to 1/3. Minus 4/3 is minus 3/3. Oh. So this is actually, if I did it correctly, just the vector 2 minus 2 minus 1. Yeah? Which we can then turn into a unit vector. The corresponding unit vector would be the vector 2 minus 2 minus 1, scaled by the magnitude, which we've already seen now is 9. The square root of 9 is 3, so scaled by 1/3. So now it's a unit vector. Yeah? So we started out with 3 vectors that were not at all orthonormal. I mean, you take 2 of these guys, you dot them together, you're not going to get 0. Here you get like 3 and 4 is 7 minus 4, it's 3, it's not 0. But now with these 3 vectors, you take any 2, they dot to give you 0. You take anything with itself, it dots to give you 1. So nice orthonormal basis. Okay. Actually, something a little bit stronger is true. I mean, like, there's an obvious orthonormal basis for this. Like, if you convince yourself that these are linearly independent, the orthonormal basis would just be 1, 0, 0, 0, 1, 0, 0, 0, 1, right? So it's like, how is this basis any better than that? Well, in some sense, it's like this is the orthonormal basis. That's as close as possible to the basis you started out with. So actually, something a little bit stronger is true. Well, it's not just that this is an orthonormal basis, but that U1, well, this won't make too much sense when you're just working with one vector, but you see how it generalizes, is a basis for the guy that's just the first vector, for just the span of V1. Oh, I'm sorry, I should have said orthonormal basis. Orthonormal basis. Orthonormal basis. Now, it doesn't really make much sense for a single vector to be orthonormal, except that it's a unit vector. So all we've done is turn that into a unit vector. But then when we had U1 and U2, that becomes an orthonormal basis for the span of V1 and V2. And then when we took all 3 of them, U1, U2, U3, that's an orthonormal basis for the span of all 3, V1, V2, V3. So it's actually quite a nice process where it's not just that at the end you end up with an orthonormal basis, but every step along the way you have an orthonormal basis for the span of the vectors up to that point. So this is a property that comes out to be useful a number of times in linear algebra. You want something like this, and this is what it's giving you. I mean, we can try and draw a picture of this, right? It's like, I'm going to have a very hard time trying to draw these, but it's like, okay, if you just have your V1 is just some vector, right, like this. And what we have now, it's like, well, the first step is really just turning that into a unit vector. I don't know, shrink it down by whatever we did, like a third, right? Unit vector. And then what happens when you throw V2 into the mix? Well, V1 and V2 together, expand some plane. And it's like, yeah, but V1 and V2 are not orthogonal to each other. So that's when we got this, turn that V2 into this W2. So this was like our V1. This was our V2. We turned that into W1 and W2. And so it's like W1 and W2 are filling the same plane that V1 and V2 were filling, right? And then finally, you had some V3, and I don't know what he looked like. I'm trying to point that he's coming out of the plane, but not necessarily orthogonal to the other guys. Some v3, and so then we say, okay, let's turn that into a unit vector coming out of the plane, w3, where all of these are mutually orthogonal to each other, right? These are all, kind of hard to draw that, all mutually orthogonal to each other. Yeah, so nice process. Okay, but it turns out there's something else. And so instead of listing these original guys as just 3 vectors, what I want to do is I want to think about them as being put together into a single matrix. 1, -2, -2. 3, 2, 2. 3, -2, 1. And then you can look at your resulting vectors, and we can stick them into a matrix as well. So they tend to have this like 1/3 up front, so let me pull out the 1/3. And here we have 1, 2, -2, 1, 2, -2. Here we have 2, 1, 2. And here we have 2, -2, -1. Like, stay with me, we're going somewhere. Somewhere really cool. Okay, so let's talk about these 2 matrices. 1, they're obviously different matrices, right? It's not the same matrix. But 2, one of these matrices is infinitely superior to the other one. Which one is that? Right. What kind of matrix is this? What was the special name we gave it last lecture? This is a unitary matrix. This is some unitary matrix. We denote it by U, some unitary matrix U. And it's like, why is U so nice? Because unitary matrices have lots of nice properties. So remind me some of the properties of unitary matrices. Yeah, if I want to calculate the inverse of a unitary matrix, well, it's just equal to, in this case, it would just equal its transpose. If working over the complex numbers, you need the conjugate transpose, right? But here over the real numbers, it's just the transpose. So it's like, try and find the inverse of this matrix. It's a pain. You have to do the whole, I don't know, crisscross, whatever you do in your first course linear algebra. But this one, very nice to find the inverse of. And there are other properties as well. We talked about, so like a corollary of this, or something equivalent to this is just saying that U transpose is the identity matrix. Like that's quite nice. There's lots of nice things, but a main one is its inverse is just equal to its transpose. Okay, good. Here's the big reveal. These matrices are not the same, but they're not so different. This matrix is your unitary matrix times another matrix, which is pretty nice. That other matrix is going to be an upper triangular matrix. Upper triangular. We'll call it T. So recall what I mean by upper triangular is I mean below the diagonal, everything is 0. And the values of this upper triangular matrix, where does it come from? It's already in here. It's already kind of standing at you, popping out at you in the Gram-Schmidt. It's things like this, and this, and this. It's these terms. It's these kinds of inner products between your new vectors u1, u2, u3, and your original vectors v1, v2, v3. That is, in particular, you can think of it as a grid. u1, u2, u3. Up here I'll have v1, v2, v3. And these entries will just come from doing u1.v1, u1.v2, u1.v3, u2.v2, u2.v3, and u3.v3. So like, what are they? What's u1.v1? Well, like, we can calculate it really fast. u1.v1, some of these we've already calculated. Like, we've already done u1 and v2 and u1 and v3. That's 1 and minus 1. We've already calculated these to be 1 and minus 1. Let me do it in white. We've already calculated these to be 1 and minus 1. And what's u1.v1? Well, u1 and v1 gives you, this is 9 times a third is 3. What's u2.v2? u2.v2 is 6. Oh, numbers are hard. 4, 6, 6, 12 divided by 3 is 4. Is that what you're getting? Okay. There's like lots of brain power here, so we need to like do some kind of distributive computing power where it's like we all work together on these. And u2.v3 is this guy right here. We've already done that. That was 2. And u3.v3, where's my u3? Ah! We called it u1. What a blasphemy. That's a u3. So, you know, u1, u2, u3. u3.v3 is 6, 4, minus 1. That makes it 9 divided by 3 is 3. So I think that's the matrix. So like, you should check this, right? Like, I don't know, first row times first column, dot those, it gives you 3 and 1 is 3, divided by 3 is 1. Or like, middle row, middle column, 2 and 1 is 2, 1 and 4 is 4, that gives you 6 divided by 3 is 2, 2. Seems like we're on the right track. Like, bottom row, right column, 2 plus 2 is 4, minus 3 is 1. What? Oh, 2 plus 4 is 6, minus 3 is 3, divided by 3 is 1. So this is correct. So this is called the QR decomposition of a matrix. In particular, any matrix, let me give it some name. I think M is fine. Any matrix M, that's a M by N matrix over some field F, where we call that field as either the reals or it could be the complex numbers, can be written as that matrix M is equal to a unitary matrix times an upper triangular matrix. So where U is unitary, that is, it's a matrix equal to its conjugate transpose, T is upper triangular, and like, what are the values of T? Well, they're exactly as described above, right? Like, if you have the columns of M will be like U1, U2, U3. The columns of U are V1, V2, V3. And T is where you get from dotting those together as above, right? Let's just note the dimension of these guys. Notice it doesn't have to be a square matrix. If this is an M by N matrix, if U is unitary, it's a basis. So if it's a basis of Fn, it must have n vectors. So that must be a square matrix. In particular, it must be an M by M matrix for us, which means T then is an M by N matrix. What do I mean for an M by N matrix to be upper triangular? So like, just note, what if I have something like a 2 by 3? Right, like some matrix of values like this. Well, to be up a triangle, you still just begin going down the diagonal, and just everything below it are zeros, right? So these are whatever values, and everything below it is 0. So that's what I mean by upper triangular if it's not a square matrix. Or it could be like a 3 by 2 matrix, or a 2 by 3 matrix. And so you just go down the diagonal, so this would be considered upper triangular. Right, you just go down the diagonal and everything below it is 0. Okay. So there are two directions we could go at this point. One is I could prove this to you. And essentially we have to kind of do what we just did, but in general, and argue it always works out the way that it works. And there's a lot of keeping track of notation. And it's a good exercise. But I think what I'd rather do is spend some time talking about why this is significant and why this is a powerful thing to do. So why do we want to do stuff like this? Well, we've kind of already let the cat out of the bag when we said unitary matrices are nicer than other matrices, and the fact that it's easy to calculate their inverse, right? So like, if you have some situation where you need to calculate inverses of a matrix, maybe this is a good way. If you could write the matrix first in this form, it would be easy to find inverses of it. Now granted, doing all this step to move it from here to here is a lot of work. And so maybe if you just want to find the inverse of a matrix, this isn't the way to go. But there are some problems where you have to find inverses lots and lots of times. So for example, suppose you want to solve some system of equations where it's some matrix times your variables x, y, z gives you some output values. The way you solve this is you have to find the inverse and move it over. And you can do it that way. But let me show you another way. So for example, suppose you have your original matrix as the matrix you have here. So your system of equations is 1, 2, minus 2. 3, 2, 2, and 3, minus 2, 1. And you're multiplying this by some x, y, z. So this is really a system of equations, right? 1x plus 3y plus 3z is equal to whatever it's equal to. 2x's plus 2y's minus 3z's is equal to whatever. Let's just say it's equal to 1, 2, 3. Negative 2x's plus 2y's plus 3 plus a z is equal to 3. A system of equations. What we're going to do is instead of finding the inverse and moving it over, we're going to say, well, this is the same thing as your unitary matrix times the upper triangular matrix times x equal to b. And the unitary matrix is nice because its inverse is just a transpose. So that's the same thing as saying that Tx is equal to U transpose B. And so notice how this plays out. What is your T? 3, 1, is that 4? No, 3, 1, minus 1. Thought we had pi for a second. 3, 1, minus 1. 0, 2, 0, 4, 2. 0, 0, 3 times x, y, z. This isn't going to be bad. This is just going to be, okay, some combination of x, y, and z, some combination of y and z, and some combination of z. But we're going to see that it being up a triangular actually makes our life really easy. See that in just a second. Is equal to U transpose. So we know what U is, so it's not hard to find the transpose. The transpose is just going to be switching your rows with your columns. So the first column now is 1, 2, 2. The second column is 2, minus 1, minus 2. Yeah? No, 2, positive 1, minus 2. And the last column is minus 2, 2, 1. And we will multiply that by b, where that's here, 1, 2, 3. Okay, so go ahead and do this out on the right. And like, what do we get? 1, 4, that's 5, minus 6, that's negative 1. Here we have 2, 2, so that's 4. And 6, so that's 10. Am I right so far? Good? Yeah? What's wrong?
The last row should have a minus 1 here.
Good call. Yeah, that's right. The last row becomes the last column. Yeah, I think we're good. And here we get minus 4, minus 3, that's minus 7. And 2, so that's minus 5. Did I do that well? I think so. So now what you're really trying to solve is this guy. He is equal to him. But like, this is not a hard thing to do, because you just have 3z is minus 3/5. Right? So the bottom just tells you that 3z equals minus 3/5. What's the form of dyslexia where you put the top and bottom opposite? Surely there's like some thing for this, right? Anyway, minus 5/3. And so then we immediately recover. I'll do it in bold. Z is minus 1/3. And then it's like, once you have the bottom, now we can go up a row. We have 4 copies of y. Did I do it wrong?
5 divided by 3.
Oh! I definitely have the upside down dyslexia thing. 5/3 minus 5/9. Right? Is that where we're at? Good. 4/3 plus 2z, but I know what z is. Plus 2 times minus 5/9 should give me 10/3, right? 10/3. And now we can solve that. So it's like, how do we solve that? Oh, I don't know. We're adding 10/9 to 10/3. 10/3 is 30/9, so we have 39/9, which sounds a whole lot like 13. So I think y is 13/4. I have no idea. Did I do that right?
It's 40/9.
What? Okay, so this is 30/9, and we're adding to it 10/9. So that's going to give us 40/9. And then we're going to divide that by 4, so that gives us 10/9. Right? Okay. You can program a computer to do this. This is the point of what I'm saying. Is like, this is computationally easier than actually find the inverse of this matrix. Right? And then the last step is, now that we know z and y, we can say, what is this top row going to give me? 3 copies of x plus a copy of y, so plus 10/9, and then minus a copy of z, which is minus minus, so plus 5/9, should come out to equal a -1/3. Oh. So here we go. Minus 3/9 minus 5 minus 10 is minus 18/9, which is -2. Divided by 3 is -2/3. So x is -2/3. Okay. We have no idea if that's correct or not, but if, that's the procedure. I think those values are close to being correct. And so we've solved x, y, z to be 1/3 of -2. Oh, I shouldn't have done 1/3. 1/9 of -6, 10, and -5. There's your solution. Or up to human error. Okay. Well, that's an example of how we can use the fact that it's very easy to find the inverse of u, and then t isn't too hard to deal with in the end, right? So unitary matrices are nice to work with. Let me say one more thing about why this might be nice. I mean, one question you might ask from the get-go is like, how do we know if a matrix is invertible? Well, to do that, it's like if there's only going to be a solution if this is invertible. It's only going to be invertible if the determinant is non-zero. So is there like some way we can hack this to figure out the determinant? Well, let's think about that. Of course, it only makes sense to find these inverses and ask about the determinant when you're in the square case in m by m, right? So let's say we're in that case. So if we have a square matrix M, then M can be written by a decomposition as U times T, where U is unitary and T is upper triangular. And these are both square matrices now, right? Everything's a nice square matrix. So like if this is a n by n matrix, it's going to be equal to an n by n times an n by n. Okay. And let's say we want to say something about the determinant of M. Our question is, what is the determinant of M? Well, that's just the determinant of ut. And do you remember what's the determinant of a product? That's right. It's the determinant of u times the determinant of t. And like, let's come down here and think for a second. What's the determinant of u for a unitary matrix? What is it? 1. Why would you say 1?
Because it is equal to its, yeah, if you take the conjugate transpose, it should be its inverse.
Okay, so you're saying that since u inverse is equal to u conjugate transpose, yeah, then what?
Well, the inverse, so the determinant of the inverse is equal to 1 over the determinant of the original.
So now you're saying the determinant of u inverse is 1 over the determinant of u, but you've just told me that u inverse is the determinant of u conjugate transpose. Now what?
I think the determinant of u conjugate transpose should be determinant of u.
Ooh, what does transpose do to the determinant? Transpose, what is the transpose going to do? Like, let's just remind ourselves really fast. If you have some matrix, I don't know, A, what's the determinant of A transpose? It doesn't change it, that's right. That's just the determinant of A. How about the determinant of the conjugate of a matrix? If you're working over complex numbers. If you're over real numbers, it doesn't matter. But over complex numbers. When you think about it, this is just taking the conjugate of everything inside of A. And then you think about what the determinant does and how you calculate it. It's like, well, I've taken the conjugate of all the pieces. Taking the conjugate of a product is taking the conjugate of each piece. Taking the conjugate of a sum is taking the conjugate of each piece. And since the determinant is just a product and sum of all the elements, and you've taken the conjugate of all of them, you just end up with the complex conjugate of the determinant. So putting those properties together, the determinant of the conjugate transpose will equal the complex conjugate of your original determinant.
So we have that we have the magnitude of our complex.
Good. So we have that the determinant of u times its complex conjugate is equal to 1. So we're thinking about determinant of u as possibly being a complex number. If you're working over the reals, it's just saying that this thing squared is 1. But if you're working over the complex numbers, this could be something like, some a plus bi times some a minus bi. So when you multiply those out, you get a squared plus b squared is 1. What is a squared plus b squared? Well, that is the magnitude of the determinant squared is 1. This is a complex number, and the magnitude of a complex number is the square root of a squared plus b squared. So this just tells you that the magnitude, or you can think of it as absolute value, but for complex number, this is the square root of a squared plus b squared. Will have to come out to be plus or minus 1. Oh, well, if I'm taking the magnitude as 1. Okay, great. The determinant itself is, plus or minus 1. But the magnitude of the determinant is 1. So, well, the determinant itself is something with magnitude 1. Suppose in principle it could be something like root 2 plus root 2i. Root 2 over 2 plus root 2 over 2i, right? Because that also has magnitude 1. Okay. But its magnitude is 1. So maybe what I should talk about then is the magnitude of this determinant, is the magnitude of this determinant, is the magnitude of this determinant times the magnitude of this determinant. And the magnitude of u is 1. How do you find the determinant of t? You just multiply the diagonal entries. So this would be equal to the magnitude of the product of the diagonal entries. I'll call them like t11 times t22 times t33 up through, tnn. But we know what those guys look like. Those guys are exactly these diagonal values. So this just comes out to be the magnitude of your matrix is just found by doing the inner product, or in particular for us here, the dot product of u1 with v1 times the dot product of u2 with v2 times the dot product with all the way up through un with vn. And note the magnitude is 0 if and only if the determinant is 0. Right? So as long as this magnitude comes out to be non-zero, you know your matrix is invertible. Here my u1 through un are the columns of u. U has columns u1, u2, up through un. And we call v1 through vn were the columns of your original matrix. Okay, so if you can write a matrix, or you can, but if you go ahead and do it and you write a matrix as a unitary matrix times an upper triangular matrix, you have a nice way to calculate a determinant and to solve systems of equations. And this is kind of a transition where we're going to be headed after your exam, where we're going to be looking at lots of other kinds of ways of decomposing matrices. Right? Like, here's one way to decompose it, a unitary matrix times upper triangular matrix. These matrices have nice properties, therefore we can do cool tricks. Where we're headed is we're going to look at lots of other kinds of ways to rewrite a matrix or decompose a matrix into two other matrices that have nice properties. And we'll talk about how that lets you do various tricks and solve various kinds of problems. And various decompositions will help you with computational efficiency in various kinds of problems. So that's kind of where we're headed in the course. But that'll be after your exam next week. Okay, let's stop.